Hey guys, it's Solbyte, and today I'm going to be going over hash tables. So what exactly is a hash table? Well, it's a data structure that allows us to store key value pairs and access those key value pairs in an efficient manner. So, um, and the way that this data structure actually works is we're basically going to have an array of what are called buckets. And these buckets are going to be where we store a key and a value, right? The actual key value pair, all right? And we will insert, the reason it's called a hash table is we will insert these key value pairs by running the key through what's called a hash function, right? Which the hash function, sorry, basically all that it does is it turns our key into an index. So that way it can access or it can go through the array and we can insert things, we can remove things using that index that spits out from the hash function. And there's different ways to do the hash function, but the most common way is going to be the one that we're going to be using today. So yeah, and one other thing I kind of want to definitely go over, one crucial thing about hash tables before we kind of begin is the fact that, for one, obviously it's an array, so it's a fixed size. And what this means is that sometimes we can have keys that produce the same index number after it goes through the hash function. And this would be called a collision, right? And there's many different ways of dealing with the collision, but today we're going to be using something called separate chaining, which basically just means that each bucket in the hash table is a linked list, right? So we're going to be creating a linked list, and basically we're going to be having an array of these linked lists, essentially, is what the hash table, or what our hash table will look like. But there's some different ways that you can implement it, but the most common way is to do it like this. So basically, if a collision happens where, we need to access something from a certain index or whatever, then we basically just chain the two key value pairs in one bucket. That way we can still access the key value pair that we're actually looking for without having to increase the size of the array, because the larger the array, the more inefficient it is to search through the hash table. And that's kind of the entire point of hash tables is they're mainly used for having large amounts of data, and they're used so that way we can search through that large amount of data efficiently. So anyways, let's go ahead and start with the implementation. I'm going to include some videos, some extra videos and some extra like diagrams that kind of go over the entire concept of what a hash table is. Usually in most of my videos, I kind of just focus on the implementation of a hash table. So I do recommend going and seeing the things that I left in the description, or if you already know what hash tables are, but you don't know the implementation, especially in C++, then, you're in the right place. So, all right, so let's get started. So firstly, let's go ahead and create a struct, the node struct. And if you guys have seen my linked list video, you'll know that this is not something that is new. We're going to create some nodes, and these nodes are going to have three things. All right, so usually we have it, or in a normal linked list, we just have it have a value, and we have it have the obviously the next pointer pointing to the next node in the linked list. But here, since we're creating a hash table, we're also going to include a key in each node, because we're going to be storing a key value pair for each node. So we're going to have a key, and we're going to have the actual value, which today I'm just going to use the example of a string. So an integer for the key and a string for the actual value for the key value pair. And then obviously we want to create a next pointer pointing to the next node. All right, and then really quick, let's also go ahead and create a constructor for this. So we're going to pass in the key and pass in a value for the constructor, and we're just going to set the value equal to, set the key equal to the key from the parameter, and the value equal to the value in the parameter. And then for the next pointer, we're going to set that equal to just a null pointer for right now. All right, perfect. So this is going to be our node struct. We're going to be using this for the actual linked list. All right, so perfect. And now what we're going to do is we are going to create the actual hash table. And I mean, you can do a hash table in different ways. I mean, you can just do it in a struct, but you know, I like using classes personally, so I'm just going to be using a class for this video, but there are different implementations. In fact, I already know one of the examples that I'm going to be including in the description actually has an example where they don't even use a class. They just use multiple different functions and structs to kind of get the job done for the actual hash table. But for me, I like to just kind of have it in a class. And usually if I was making a full-blown project, I would use header files and all this kind of stuff. But, you know, for the sake of simplicity, we're just going to have it all be here. So I'm going to create a class called hash table. All right, we're going to have some private member functions and public as well. All right, and so in our private members, we are going to include two things, only two things. One is going to be the capacity of the hash table. The capacity is just how much can be stored there. And for that, we're going to create a static const integer. All right, we're just going to name it buckets. And I'm going to set it equal to 10 for this example because it's a pretty common example for most people to use when going over hash tables. So we want it to be static. I know I haven't really used static or non-static or whatever too much in my tutorials, but we're going to use static because of the actual hash table. We are going to create the an array of pointers pointing to the buckets. Okay, and to do this, we need to make sure that buckets is a static variable. So we're going to do node table buckets. Okay, and there we go. So this here is, I guess, technically the actual hash table itself. We are making it of size 10, whatever the buckets is. And I mean, I guess we can maybe make this kind of dynamic for the user to decide. But I'm not really going to go into that for this example. But yeah, so these are kind of the main parts of what actually creates the actual hash table itself. So nice. All right, and so now, you know, we've created the actual variables needed for the actual hash table. One of the more important things that we should do right at the beginning is include a constructor. All right, so we're going to do just a hash table, just like we would do for a normal one. And what we're going to do inside of this is we are going to do a for loop that iterates over the hash table. And the reason that we want to do this, the reason that we want to actually do this is because we don't want, whenever a hash table is actually created, we don't want these pointers to point to nothing. We don't want them to be just garbage values. In fact, it'll actually throw up an error, not a compile error, but a runtime error. So the way that we avoid this is we go ahead and we set each bucket equal to just a null pointer. All right, so they just point to nothing at the very beginning, whenever you haven't inserted anything or deleted anything. So perfect. And then the next very important thing is going to be the actual hash function itself. The way that this works is we need to create a function that allows us to pass in a key, and this key we need to convert to an index number. The most common way of kind of doing this is just returning the key modulus 10, right? So if the key is 105, doing this will return 5, and therefore it can be an index number in our array. So pretty common example. There are some different examples as well that you can go and check out. I think the one of the examples that I include in the description actually kind of goes over a different or multiple different implementations for that matter. So definitely go and check that out if you're interested. But this is kind of just a very common and a very easy hash function. So this actually allows us to have our key convert into an index number that allows us to, that allows us to access, insert, remove whatever values, whatever key value pair from that specific index or bucket. So nice. So we have two very crucial, two very simple functions to kind of get our hash table started. So we're gonna go over. I think we're gonna do 3 functions today. We're gonna do 3 functions. There's more functions that you can do with the hash table, but I'm gonna go over the 3 most important functions for a hash table, and that includes inserting, removing, and searching. All right, so first let's do the insert function. So let's just do void insert, just make it kind of simple. And whenever we pass in something for the insert function, we'll need to obviously pass in a key and whatever value we want to insert as well. So there we go. Now, the first thing, the most important thing that we'll do basically for every single function in the hash table is we need to actually convert whatever this key parameter is into an index that we can use for the hash table. So the way that we can do that is we can do int index, create a new integer variable called index, and we will convert it to an actual index using the hash function right above here. So we'll do hash function, there we go. And we'll just pass in the key. And what this will do is it'll allow us to have an index that we can use to go over the actual hash table. So, all right, cool. And so now that we have this index number, what we want to do next is we want to be able to traverse through the hash table and find exactly where we want to insert this and actually insert it. So the first thing that we really want to kind of check is if something is already in that bucket. Like I described earlier, collisions can happen. So the first thing that we can actually, or that we would actually want to do is check if this index happens to cause a collision, and therefore what do we do if we want to create something new, right? So the way that we can do that is as follows. So first, I'm just going to set a node pointer, and we're gonna do, I think, head. Yeah, head. We'll do table index. All right, so we're just creating a head node pointer, and it's going to start at the index for the hash table. All right, so this is just us getting the head pointer at wherever this index is. So there we go. And now we want to create another node pointer that we can be able to iterate over in a little while loop down here. So now we want to actually traverse through the linked list for the bucket and check where we need to actually insert this thing. So we're going to first, of course, just check that current does not equal a node pointer. All right. So now we'll do a couple of if statements here, do a couple of conditionals. We want to check for each iteration through the while loop as we traverse through the linked list for each bucket. We want to check if the current key matches the key from the parameter. And if so, all we need to do from that point is just insert the value for that key. Or sorry, wait, I need to, there we go. There we go, all right. And then we can just return out of this because nothing else is needed. So, perfect. And then of course, down here at the bottom, we want to make sure that we are actually traversing through the list. We'll just do current next, right? And now we need to handle if there is no node, or no actual, basically nothing inside of the bucket, no nodes, no linked list, no nothing inside of the bucket. What happens if there's nothing, right? So then we would need to actually create a new node inside of that bucket and fill in the values from there. So the way that we can do this is we can first start by creating a new node. So we'll just do new node equals new node, and we will set it, make sure that it's constructed properly. There we go. And now the next thing we want to do, just as a good check, is we want to set the new node next pointer equal to the head node, so that way it inserts at the very beginning of the list, no matter what. Just a good check. for that. So, and then after that, we can simply just add table index equals new node. All right, so perfect. All right, so we are now done with the insert function, and I do want to actually showcase how this, is working. So what we'll do is we'll go ahead and just jump straight to the search function. The search function is actually pretty easy, so don't worry. But so this will allow us to actually look up some things in the hash table. So I can actually, create a hash table down here, and we can insert something, and then I can search it up and see that it is actually there. So let's go ahead and do that really quick. So like I said, first thing we really need to do in all of these functions is actually hash the key, so that way we can have an index that can go over the array. And then next, we're gonna need a node pointer that allows us to traverse through the actual hash table. Okay, and then now let's actually traverse through it, just like normal. So we'll do while current does not equal a null PTR. We will check if the current key matches the key from the parameter, so kind of just like the insert function. And if it does, then in that case, we will set the we won't set it to anything. We will return the current value. All right, so cool. And then down here, of course, we need to make sure that we actually do traverse through the list. So we'll do current equals current next. So, and yeah, that should be just about it. I think if we find nothing, it's good to just kind of do a little not found down here, just in case. So, all right, cool. So let's go ahead and actually test this out. Let's create a hash table. So I'll just do hash table, call it H. All right, and what I'll do is I'll just insert something. So I'll insert something at 105. That'll be our key. All right, and I'll just enter the name Solbyte. All right, so now I want to search through the hash table, and I want to do this by using the key that we used for Solbyte. So we'll do search 105. So what value is at 105? Well, let's see. We'll go ahead and see out that really quick and see for ourselves. So let me go ahead and open up the terminal and run through this really quick. All right, and there we go. We get Solbyte. And just for example, if I did 100 here, and I did this again, we see that we get not found. So perfect. We were actually able to insert Solbyte. We were actually able to insert this key value pair into the hash table and search through it using our search function, our super simple search function. So nice. So now let's go over removing a key value pair from a hash table. And from there, that's kind of the basic gist of what a hash table is. So let's go ahead and go down here. And we want to do, oh, sorry, wait, this is not where we need to be. We need to be up here, sorry. So let's do void remove. All right, we'll just pass in a key. All right, and then for here, we need to, of course, do the same thing. Create an integer index and hash the key to generate that index. All right, and then we're going to use two different node pointers. I always say node, I don't know why. So we're going to use two different node pointers, one of which being the current pointer, and we're just going to set that equal to the table index. All right, and then we're going to use another one called previous. All right, because we want to check for something to make sure that we don't completely destroy the linked list, right? And for right now, we're just going to set it equal to a null pointer. All right, so if you guys saw my my linked list video where I went over insertion, deletion, and traversal, we're going to see a very familiar thing here. So what we want to do, removing a key value pair from a hash table, and removing an element from a linked list is a little difficult, or not difficult, but it can be kind of, you need to make sure that you don't just totally destroy your linked list, right? And the way that we do that is obviously by first off using these two pointers here, because what we need to do is we need to check if the current, or if the key is pointing to, what did I just do? If the key is referencing a head node in that bucket, Or if it's not, then that means that we need to kind of change the next pointer for that element, or for the, the previous element, to equal the current next pointer. So that way we don't break anything. All right, so the way that we're going to do this, first off, is just like normal. All right, so we're just going to make sure that current does not equal a null pointer. And then we're going to do a check if the current key equals the key from the parameter. So now what we want to do is we want to do those checks. And the way that we do that is we do it with more conditionals. So we're going to do if, basically if the previous node pointer still equals a null pointer, then we know that this current node in the bucket is the head node. And if that is the case, then we just need to ensure that the current bucket, sorry, it's kind of hard to explain. The current node from the bucket is pointing to whatever the next pointer is, right? So if it is the head pointer, then we want to make sure that we don't destroy the linked list. So that way we need to basically set the current bucket equal. Yeah, I mean, it's easier for me to type it out. I don't know why I'm trying to explain it. I'm terrible at explaining. I don't know why I do these. So the current table index, right? So the current bucket that we are currently in, we need to set it equal to the current next pointer, right? So that way the next pointer basically will be the head node for this, right? So that way, if there is, because basically we're doing this in case there are nodes, or if there are other key value pairs further along in the list, but of course we need to delete the node or the key value pair here in this current iteration through the bucket. So the way that we do that is we do that with this, basically, is what I'm trying to say. So then we do the else conditional. So if the previous node pointer does not point to a null pointer, then in that case, we are going to set the previous next pointer equal to the current next pointer. All right, so we're basically making sure that the two key value pairs that are right next to the actual key value pair that we're trying to remove can link to each other before we actually delete the key value pair that we're supposed to. All right, so now we can actually do the deletion part. So we can do delete current, all right, and then just return. So nice. So this is all just making sure that we don't break the entire linked list after removing a key value pair. All right, and then of course we need to make sure that we are actually traversing through. So we're going to do current equals current next. But before that, of course, sorry, I almost forgot. We need to set the previous node equal to the current node after each iteration. So that way it's following the current node, if that makes sense. So perfect. And this should be just fine. I don't think I'm missing anything. So let's go ahead and try this. So we have inserted Solbyte. We have searched for it. Let's go ahead and do this really quick. And let's make this a little bit more clear as we go through this. So let's do before removing 105. So that way we can see the before and after. Oh, what the heck? All right, and then we will actually do the remove, and we're just going to pass in the key for where we want to remove something. All right, and then we can just do the same thing, I think. So let's just do this, let's just do this, and let's do after removing. All right, so this should return not found. All right, so let's go ahead and see this in action. I'm going to go ahead and compile and run it. So, oh, I did, why did it print like that? Oh, because I didn't add any spaces. Hold on. Just to make this a little bit more clear. It did work. It did work. I just want to make it a little bit more clear. All right, so before removing 105, it does return Solbyte, but after removing 105, it says not found. So perfect. Our removal function does work. And then for the last example, I'm just going to show whenever we do insert something with the same index. So I'm going to pass in 205, and I'm just going to pass in Austin. All right. And we're going to see us searching for both. Let's just, let's do, hold on, do 105, and then let's do, down here, we'll just do 205. Just so that way you guys see that our collision methodology is indeed working. So these would collide because a little simple trick is whenever you do a modulus 10 on a number like this, it's going to return the last number of the key. All right, so we should have the same index for these two guys. So the way that we're going to do this, I'm just going to go ahead and show you guys. So we get 105 Solbyte, which is correct, and we get 205 Austin, which is correct. So perfect. All right, and that's about it. So hash tables, they seem very complex, but once you kind of, get your toes in the water, and actually start playing around with them, they become a lot more easier to understand. And especially if you know about STL, if you know about the standard template library, you can actually implement them a lot easier than I implemented them. But I haven't really gone over the standard template library all that much, so I kind of just avoided that and just did it with pure linked list implementation. So, but there are much easier ways that you can actually implement this. And I do highly recommend looking at the resources that I included in the description. Please go and look at those. And as always, if you guys have any questions, please let me know in the comments below. And that's about it. So thank you for watching.